Hi everyone, thanks for coming and thank you for waiting. My name is Jack Porter, I'm the Unreal Engine 4 mobile team lead, and today I'm going to introduce some details behind the Chaos demo and the Chaos physics system, which is the future of physics and destruction in Unreal Engine 4. So the session is divided into 4 parts. First of all, the physics and destruction features that are going to make designing games really exciting and the kind of things you can do with game design. I'm going to discuss about how an artist would set up some of these new physics features that we're enabling in the Chaos demo. I'll talk a little bit about the technology behind the Chaos demo, and finally I'm going to talk about some of the Intel compiler tools that we're using to make Chaos fast. So what is Chaos? Chaos is Unreal Engine 4's upcoming physics system, and we're going to ship a preview version of it in 4.23. And it's going to do everything that you expect out of a physics system, including rigid body physics, vehicle physics. So it's going to completely replace the existing physics solution we're using at the moment, but it happens to be great at destruction. And so to show that, we've put together a demo we also call Chaos that is going to demonstrate, the capabilities of this system. That video should play.
Breaking news. Robo-resistance leader Chaos has broken into a robo-ready research lab and stolen top-secret military hardware. A recall agent has been dispatched.
Okay, Agent 38, it's Renegade recall time. Shouldn't have hit that one. Good thing it's that holiday. She's getting away. Activate rocket boost to get after her. Uncompensated for her lack of skill and higher power per weaponry. She's on the move again. Get after that. Let's see her teleport out of that one. Now would be a good time to figure out what that thing actually does. Oh, that's not good. On the bright side, you've been approved for mandatory overtime.
So that shows a little bit that can be done with the destruction components of our new Chaos physics engine. So I'm going to go into some detail about how that demo works and the kind of things that you can do with it. So first of all, everything you saw there, including all of the destruction, was created entirely within Unreal Engine 4 without using any external tools. So everything you saw was created using Unreal Ed. And the second thing is that everything you saw there was rendered completely in real time on a high-end gaming PC. Not only that, everything you saw was simulated in real time with one small caveat, which is it was simulated in real time when needed. And I'll go into some detail about what we mean by that by giving you some examples of the 3 scenes in that demo. So in the first sequence, you're chasing this little robot, and everything here is simulated in real time, and it needs to be because we can't know where the player is going to shoot. So depending what they shoot, we're going to destroy those particular elements. And so everything needs to be destructible. And in the second sequence, everything is also simulated in real time, both this initial building here, as well as this larger building here, the Robo-Ready headquarters. That's pretty amazing that you can simulate that kind of destruction in real time. And when we get to the third section here, this one's a little bit different. This is a cutscene, and we're destroying an entire city block, and here we're playing a pre-simulated destruction of the entire building that we're playing back from a cache. And this might sound like the first two examples and this example are completely different, but that's not the case at all. So in using the chaos system, destructions can be either pre-simulated and saved out and played back. And this is great because it allows us to art direct. So we can choose exactly how the destruction is going to occur, and it's going to be consistent every time. We can make the demolition look exactly how we want it to for the best artist control. And of course, it allows it to run at super high performance. But unlike, for example, simulating this in Maya or Max and then exporting that into Unreal Engine, that entire building destruction was created with exactly the same tools as the rest of our chaos demo. Everything's based on this new actor type I'll talk about called geometry collections. But most important is that any of the pre-baked simulation can become active at any time. So if we wanted to, we could approach all of the debris that was created from the entire city block being destroyed, and we could shoot at it and all the pieces would fly around as you'd expect. And that wouldn't be possible using a traditional way of pre-baking physics simulations. So the destruction is never static. And this means you could use it for a game design situation where, for example, you could stand under that building as it's collapsing and you could be shooting each of the pieces that are falling on you, and you could destroy those pieces and prevent yourself from being damaged. So that level of control, even though the rest of the simulation, the parts you're not shooting at, is all cached, that simulation can be extremely performant. The rest of the simulation is happening by being played out of the cache. And this really hasn't been, this kind of interaction with huge simulations has not been possible in the past. Normally you'd have to divide what the player can interact with what's pre-baked. So Chaos is a first-class citizen of Unreal Engine 4. And so it lives alongside all of the other systems that you use for gameplay. So you can trigger it using blueprints. You can query it for the state of the destruction or the state of the destructible objects. And you can send events to it, which means all of the gameplay systems in Unreal Engine integrate very tightly with it. And so, the great thing about having all this destruction is it looks awesome, but you need a way of controlling that so your game doesn't get out of control. Because demolition is messy, it's unpredictable, and if it's player-driven, it's going to play out differently every time, and the player adds uncertainty. So we've added some runtime systems that let you control that amount of chaos and destruction that's going on to allow you to control parts of your gameplay. So as an example, in the editor here we have this thing called a kill field, and any physics object that falls into this volume, which we use volumes to represent fields in the chaos system, anything that falls into this field will be destroyed automatically. So if you've got a huge chunk of debris that falls into this field that the level designer has placed, it'll be destroyed into smaller and smaller pieces. And you can use this, for example, maybe after the building is destroyed, maybe the police arrive in some vehicles and you need to make sure you're not going to have a huge chunk of debris in the way. This kind of field will allow you to make sure that the gameplay is not going to be affected, or the future cutscene will not be affected by anything the player might have done that we didn't predict. Navigation is fully supported on the geometry collection actor type. So enemies can stand on any destructible geometry, and when it's destroyed, they'll fall correctly. we can have dynamic navigation mesh modified by debris. So if you have a huge chunk, you can have it fall there and update the dynamic navigation mesh, and AI will know they have to run around that debris instead of trying to walk through it. For this chaos demo that we put together, we didn't actually use that. We used a simpler approach, which is we made sure any debris that fell to the ground was small enough to be kicked or destroyed by AI walking through it. So as the robot walks through it, if she knocks or kicks any debris, she can kick it away and it'll get destroyed. But because we support dynamic nav mesh, you could absolutely design your AI to interact with larger chunks. For example, you could teach them to use it as cover. Of course, you want AI to react to the debris that falls down, and every debris event that occurs has information about the mass and the velocity, etc. So that we can use this to trigger the appropriate reaction. So here, a physics object is falling on a player, and we can tell from its mass and velocity that it has enough impact to kill the player. But you can trigger an appropriate reaction. For example, in this case, the AI has been taught, events happening nearby and to react appropriately. Or to act surprised, etc. So this is AI acting autonomously without pre-programming the events, just based on the information about a debris event occurring. For example, in this case, it's occurring above a destruction event's happening above the player's head, so they can be, or the AI's head, so the AI can react appropriately. But what about designers detecting events? So this is a little volume we created in a blueprint called a destruction detector. And its job is to listen to how much damage has occurred inside a volume and then trigger a blueprint event whenever that amount of damage or more has occurred. So we listen to that event, and we can use this to advance progression. So in the first part of the demo, because the player is shooting wherever they want, we don't progress to the next stage until the player has destroyed all of the columns. So by putting these destruction detectors around them, we can gate the progression. We could also have detected the amount of debris. Instead of the amount of destruction, we could detect the amount of debris in the volume. We didn't do that in this demo, but that would be very feasible if you wanted to do something that relied on the amount of debris. For example, here's a blueprint that counts the amount of debris that has occurred. And for this, you could, for example, you could have a big truck or container that the player needs to fill up with rubble before the game can progress, or for a gameplay event to occur. And you could easily make those kind of puzzles in your game. Finally, you can detect destruction this way, and you could do things like disable your cover nodes, so your AI will know not to use that particular pillar as cover anymore because it's been destroyed. So in this demo, we just manually looked for blueprint events and then disabled the cover nodes, but you could easily build a system using blueprints that completely automated this process. And so these are just some simple examples. We've already taken care of the difficult part, which is to connect all of the events in this integrated physics system into the existing systems in Unreal Engine. You can take care of implementing whatever interesting gameplay behaviors you like. So Chaos was built with networking support in mind. We obviously make networking games at Epic, and this is going to be our physics system moving forward, so we fully expect to have both destruction and regular physics, like vehicle physics, networkable or have network capabilities for them. This is in active development. So now I'm going to talk about the artist tools and how an artist would go about setting up chaos scenes. So what do artists want? They want, obviously they want the end result of this absolute total destruction, random fracturing, the user applying random forces wherever they want. But the most important thing that artists want is they want control over this. So they want control over the look of what the destruction as objects are being destroyed. They want it to run in real time, and they want to be able to control gameplay elements without having everything get out of control. So as I mentioned, we have this new asset type in Unreal called a geometry collection, and these are built specifically for destruction. I'll give you some more information about how they work in a moment, but some details is that for an artist, a geometry collection is built from one or more static measures, including those in separate blueprints or nested blueprints. And they let the artist choose what they want to simulate. So when we built this demo, the pillars we built out of 3 geometry collections. The lower building was 200 plus geometry collections, and the major destruction of the entire building was only 12 geometry collections. So they really optimize and allow you to flexibly organize the way your destruction is going to occur. So, of course, everything's inside Unreal Ed, so we need good fracturing tools inside Unreal Ed as well. So, there's our on the left is our original geometry collection, and then we've done fracturing across that entire mesh, and then we subfracture only those large pieces. So it's really key to mention once again that every single piece of geometry in this demo was fractured inside the editor. And you can fracture each individual part, or you can apply a single fracturing pattern across multiple pieces. So we have standard Voronoi, but we also have a clustered version which looks a little bit more realistic. We have some radial fracture and planar fracture type fractures for specific situations or specific events you might want to set up. And our fracturing system is based on levels. So you can fracture a whole geometry collection into a few big pieces at the first level, and then you can choose for each of those levels which pieces will fracture more into subsequent levels. And the chaos system stores this information into something we call a cluster that an artist can control. And this allows us to have good performance. This is an example where each fracture level is combined into a set of clusters. And the chaos solver, the physics engine that underlies the destruction, treats each node as a single object until there's been enough strain, enough force to cause a break and progress to the next level. So you can see our level 1 destruction. We're calculating only those pieces. And then at level 5, you can see that's all the leaf nodes. By tweaking our strength values, we can get a result that takes the large-scale simulation from level 1 and make sure only under particular circumstances do the larger blocks break into smaller chunks. This gives us a result that not only looks more natural than just turning everything to rubble, as level 5 does, but it also performs very well because the calculation is only happening at the appropriate levels. You can also use our auto-clustering system for artists who want a decent-looking result without having to go through the entire object and work out exactly how they want the clustering to occur. And this allows you, this is kind of a procedural flattening of the hierarchy that you can set, that will set up the clusters for you, and then you can do a pass with auto clustering, and then you can clean up some of the details if you want to. And so controlling how difficult it is for each chunk to break is a wonderful time where the performance requirements as well as art can work together to make something that looks really realistic and looks really awesome. Now, there's another concept we have called the connection graph, which is a connectivity map between different parts of the simulation. And some of the nodes in the connection graph, here colored in yellow, are anchored to the rest of the scene. So those things are never going to fall, never going to break. But the system knows that the connection graph, or it knows what parts are connected to what other parts, and therefore when you destroy enough of the connection graph and the strain passes a particular threshold in the graph, all the other parts will begin to collapse. And this can also be used to control the number of rigid bodies that you have active. The next concept we have are what we call fields. And fields are ways for us to set up everything without having to go in and specify individual properties everywhere. So fields allow you to put control directly in the hands of the artists by defining a volume where something occurs or where a property is applied. And this is one of the easiest ways artists can directly interact with the way the simulation will occur. You can control any attribute of the geometry collection. You want to vary your mass, you can put a big mass, a big volume around which will apply some mass settings to a bunch of objects. You want to make the corner corner stronger than the middle of your, weaker than the middle of your building, then you can put a field around the corners. When we shoot at the building, we're actually spawning fields that are affecting and straining our connection graph. So that's what those pink spheres represent. They're fields that are applying a force. And at the bottom there, we have an anchor field, which is anchoring the base of the building to the rest of the scene, so we don't have objects falling through the ground. Fields are created and controlled with blueprints. So in this example, we're applying some strain and then a bit of linear force. And then with some radial fall-off, we can make the strain be applied more weakly at the edges. And there's a modular system. You can stack fields together. You can multiply things. You can add noise. Anything you can imagine using blueprints, totally possible to apply to your simulation using a field. And this blueprint here is the basis for the weapon system that we're using that applies a strain on impact, but you could expand this to make sticky bombs or rockets or any kind of explosion type weapons, anything you can think of. As I mentioned, we have anchor fields. These lock the particular nodes that are covered by the fields in place. And so we've locked the top and bottom of the pillars together to control how much they can collapse. And often we use these kind of anchor fields as a base for building upon. This is an example of strain fields and force fields. With enough strain, you can break the connections. Each connection has a limited amount of strain that it can take, and so that particular volume there was applying a strain field. And the strain required to break each cluster is tunable by the artist, so you can make it so that your heavy beams that make up the building are much stronger than the windows or the outside parts of the building. And so you can do this for gameplay reasons or performance reasons or just artistic reasons. We have this concept called sleep fields. Anything that lands in a sleep field will quickly be put to sleep and have its simulation paused. And this is great if you want to, if you've got loads of debris landing on the ground and you want to stop it bouncing around when it doesn't need to, you can simply put a sleep volume at the ground and it will put everything to sleep when it lands there. So as those pieces are falling and hitting the ground, they're being put to sleep. They are still interactive, so we can still shoot them and that will wake up those individual parts of the simulation, but it looks better and is better for performance if we more rapidly put those pieces to sleep. We also, of course, automatically put any object below a predetermined velocity. We automatically put it to sleep, but as I said, sleeping objects can be woken at any time. The high fidelity simulations that you're seeing here with the destruction of the entire block can be pre-cached and then played back in real time. And this means you can author very large scale destruction events and still allow some level of interactivity with them and the environment. So I hope this gives you some idea about how artists can control these aspects of chaos. And, you know, I really look forward to what you guys can do when you get your hands on it. Next, I'm going to talk about some of the tech behind chaos and how it works under the hood. Some of the general physics features we have compared to our previous physics system, PhysX. We now support non-convex collisions. This is really key for if you've ever had to set up collision using a bunch of convex parts. We have very high performant non-convex collision primitives inside Chaos, the physics engine. We have this field system that I've just been mentioning, which is extremely powerful for making a very broad impact on the physics scene. We have very tight integration with Niagara, our new particle system. And I'll talk a little bit about how that works in a moment. We have this interactive caching, which enables a much more interactive versions of cutscenes that were not previously possible, in ways that were not previously possible. We also have a dedicated physics thread, and so this means we can decouple the physics calculations from the rest of the game. We can ticket it at a different rate, and we can completely separate the physics performance from the rest of the game's frame rate. For destruction, we have these geometry collection actors that hold together and very efficiently render very large destructible objects. We've got those in-editor cutting tools. We've got destructible LODs. The way the hierarchy system works for with clustering enables you to use the clustering as kind of LOD. And we have that dynamic strain evaluation, which is determining when things will break. So the first feature is the ability to simulate non-convex collisions without paying the typical cost we would have by joining combinations of convex objects together. And this is pretty much necessary for any kind of complicated fracture like you're seeing in the video here. As I mentioned before, you can set any physics parameters that you like using fields. We talked about this a little bit earlier, but they can be used to affect a number of different properties in the simulation, including creating constraints, sleeping particular regions of simulations, pretty much anything else. So you can combine these in interesting ways to add or subtract or modify properties to give much more interesting looks. And we also support adding noise or radial velocity to fields. And this is an example of a blueprint that we talked about earlier. This is being used to apply strain and breaking up some objects in the scene. So each collision and breaking event is directly transferred across to Niagara, our particle system, for doing dust and debris simulation. And we can also use it for other systems such as AI and audio. And you can imagine with this amount of destruction going on, you could have a lot of events occurring, and you need good ways to filter these out. So if lots of destruction is happening in a small location, we can in fact filter out the data that we pass on to the particle system, so only the largest events within particular regions get passed on. And the same, if you've got a lot of destruction going on, you only want to play audio for the largest collisions or the largest destruction events. One of the goals was to have the entire world to be interactable while still having large-scale destruction. And to achieve this, we have made this caching system to record and playback simulations at a large scale, but still allow interaction. Because we built this entirely inside Unreal Engine 4, you don't have to constantly import and export this simulation data like you would have to if you were using an external product. As I mentioned, we wanted to completely decouple the physics calculations from the rest of the game. So, for example, you might want to run your game at 60 frames per second, but run your simulation at 30 frames per second. Or perhaps physics is really important to your game and you want to run your simulation at a constant 120 hertz, but have a variable game frame rate. All of these things are possible. So as I mentioned, the destruction system is based on what we call geometry collections. And these are something halfway between a skeletal mesh and a static mesh. And they work by grouping all the triangles together with a shared material and rendering it in a single draw call for efficiency. So this building here, it's probably only got 3 or 4 materials. We can render the entire building during its simulation, no matter how it's being destroyed, consistently in 3 or 4 draw calls. And this is really important for performance, obviously. And at the same time, it's substantially cheaper than either a set of individual static meshes or a fully skinned skeletal mesh, which would have been only options previously. Our cutting tools let you break any static mesh with Voronoi, with plane cutting, or with even an image-based fracture. And using the level system we were talking about earlier, we can make levels of destruction so that as an LOD system for performance. So you can see here in the video, we've got the initial breaking of the pillar falling to the ground and then the subsequent breaking when it's being broken into smaller pieces on the ground. There you go, there's a big chunk. And this can be used as an LOD system. So by controlling which level is being applied of destruction, you can have performance on lower end devices. And so, as well as being used to control art, from an art direction point of view, you can use it as an optimization strategy. Now, all of these systems work in the destructible world, or a non-destructible but interactive one. We wanted to make sure that objects can be destroyed in a believable way, and to evaluate the strain dynamically as the world undergoes various forces was key to making this realism work. And then the connection graph adds added realism to allow things to behave like they would in the real world, so that removing multiple supports will allow something that depends on them to collapse. And the final section of this talk is talking about how we made chaos perform well. And it's something we did partnering with Intel, using some of their technology to optimize the CPU time for the very low-level solvers that are the basis for the chaos physics system. And during this development, we learned a few things. First of all, we learned that C++ is very bad at doing single instruction multiple data. So we integrated, the first thing we did was we integrated the ISPC compiler, which I'll talk about on the next slide, for around 3 times performance gain over raw C++ for critical areas. Secondly, using tset to categorize whether something is or is not a member of some certain collection you need is not very good at very high performance situations. So we found a lot of the time was spent hashing things and updating the hash as we added and removed items from the tset. And so we found it was much better to use a t-array and then to sort that t-array and use remove swap to remove items from that t-array. It's much better than testing the tset hash when we're adding and removing objects. In Unreal Engine, we use Parallel 4 in a lot of code, which automatically allows you to run an inner loop across multiple threads. And this is good for some level of parallelism, but it's possible to oversubscribe this system and end up creating a lot more, trying to do a lot more work in a lot more parallel threads than is actually useful. So we found batching things together was a much better data access pattern, especially if the data is cache friendly. So for the very small inner loops, we use something called ISPC, Intel's single program multiple data program compiler. Bit of a mouthful. But the problem it's trying to solve here is finding ways to make use of this technology we've had inside the vector units inside modern CPUs on all platforms. We've had this kind of technology since the early 2000s, but the solution up until now was to use compiler intrinsics based in, for example, Visual Studio intrinsics, or for mobile, GCC intrinsics or LLDB or LLVM intrinsics to to allow you to use these vector instructions. But one of the problems is it's really hard to turn C++ code into things that vectorize very well. And so using ISPC allows us to write code much more like a GPU shader that runs on the CPU. And this compiler has a bunch of different backends, including SSE4, AVX, AVX2, as well as a Neon backend for mobile devices. And we've integrated this into Unreal Engine 4 for use in Chaos, but also use in other systems. So if you have your own systems in Unreal Engine, you could make use of this to vectorize them. And so the way you use it is to include it in your module's build.cs project file. You add the ISPC source files to your project. It generates a C++ header for you, and you include that, and then Unreal Build Tool will handle everything else in terms of linking this together and loading the code together. So this is a huge benefit that you can write the ISPC code once and then generate this vectorized code for all of your platforms. And so we've done this to make it as seamless as possible for you guys to use this feature or this technology in your own games. So anything with very dense compute workloads, so we used it here obviously for physics intersection testing and all of the transforms that needed to be done. Anything where you've got a bunch of data in contiguous memory, for example, in a T-array, and where you don't have any data dependency between operations. So if you've got a huge amount of data that needs to have a similar transform applied onto it in a consistent way without needing to wait on the results of the previous calculation. So it works very similar to a GPU shader, but there are some differences. With ISPC, all of the lanes are running all the time, and so if you have any conditional branches in your ISPC code, they will end up, it will just mask out the branches that are not used, but they'll still be executed. Another thing you can do, which is really neat, is you can summarize the data that you have. For example, you can use ISPC to very quickly find the minimum or maximum value of an array of integers. And we use that a lot in the Chaos implementation as well. So the code on the left is the ISPC code that looks a little bit like a shader, where we declare the layout of the parameters, and this matches the layout of the data that's coming in from a T-array. And then we tell it how to process each of the values. Here we're doing some kind of color conversion on some color data that's coming in. And ISPC for Intel is automatically generating that SSE2 or SSE4 code. If you run this same code, it will be generating Neon code for a mobile device at mobile compile time. Oops. So that's everything I have today. I hope we've given you a taste of what's possible with Chaos and maybe helped you think about some interesting things you can do with this kind of system in your games in the future. So keep an eye out for it in 4.23, and also be sure to play the Chaos demo out on the show floor out there. But I'd like to take some questions if anybody has any.